What's up, guys? This is Teddy. Welcome to my YouTube channel. So, you've made it quite far in this course, but I'm not sure that you are ready for the ultimate challenge, and that is we are going to be building a Pokemon tree. This will be the ultimate test of every Pokemaster in this entire course, and I think you are up for the challenge. But for real, we're going to be building a Pokemon tree, and it's going to be a very searchable tree to insert your favorite Pokemon into and search that tree and make the ultimate searchable Pokemon list for the ultimate Pokemon master, just like you. So, believe it or not, when I was searching for trees, I was just trying to find some random tree on the internet, and this tree that I found as just, copyright free, whatever, I've actually been to this tree, and I think this tree is in Hawaii. So if you can confirm this, and I've crawled on this little part right here, this is actually really fun to crawl on. But if you can confirm that this tree is in Hawaii and which island it is, I think it's either in Maui or the Big Island. If you know where it is, drop a comment down below, because I really want to know, because it's been so long since I've been to it. But really weird coincidence, but I've actually been to that tree right there. So what is a tree? And a tree, there's all different types of trees. There's, you could Google just tree data structure, and there's probably hundreds of different types of trees, but a tree is basically hierarchical. It's a data structure that has both children, it has parents, and it's almost like an upside down family tree. There's two parents to one child, or there has to be two parents. But in tree data structures, and more specifically binary search trees, which we are creating, you have a parent, and then you have children. This is a child. This is the main parent, and there's children underneath it. And that's kind of you don't need to be a computer scientist to know that. That's really easy. And then the only other thing that you have to know is that these are nodes. These are nodes, and these very bottom nodes, there's nulls down here. That's another thing that a lot of people don't explain. Just remember that there's nulls down here. These are all nodes. It's like a parent-child relationship, and it just kind of looks like a tree. It's not that complicated. So, and then up here you have what's called a root, and I think there's all different types of ways to describe trees. There's levels, and these things are called edges, and there's leaves. But I think you could probably get away with just knowing that amount and being able to code what we're about to actually start working on. But you need to know the important aspects of what's called a binary search tree. And binary search tree is going to be the most common tree that you'll ever see. In fact, I think it's very rare that you'll ever see anything outside of a binary search tree, and they're very searchable and they're very easy to understand. And there's three rules that separate a binary search tree, and if you can understand these three rules, you're gonna have an easy time in trees, because it's really not that complicated. So each parent can only have two nodes. So right now, this tree is correct. This is an actual binary search tree. But if I went down here and let's say for some reason I added another node right here, this would no longer be a binary search tree, because there can only be two children. Also, the other thing that makes a binary search tree, and one of the reasons it's so searchable, is that it's sorted in its own particular way. So you need to kind of understand how the sorting works and how binary search trees are actually built. So here we have a 10, and it's once again, incredibly simple. The only thing you need to know is that the greater number goes over here, and the lesser number goes over there. If the number is smaller than this number, it goes over here. If it's greater, it goes over to the other side. So we start with 10. And let's just say we want to add 11. 11 is going to go right here. And let's just say we want to insert a 6. A 6 is going to go over here. And it's really, it's not complicated at all. And here is these are the numbers that we're going to actually code up and we're going to insert. And before I actually teach you the code, I just want to kind of go through and let's just build one. And this is going to like exactly mimic the algorithm that we are about to build. So if you want to build a linked or you want to insert into a tree, what you're going to do is you insert them sequentially. Obviously, it's sequential, but the very first one is going to be the node, or it is going to be a node, but it's going to be the root. And that's kind of important because because they're not linear, it kind of makes sense that you're going to build them like a tree. Like if this were a linked list, you would just insert them one after another. But because it's a tree data structure, there's rules on where that you can actually insert them, and you're going to insert them kind of on a number by number basis, and you're going to sort them, but you're going to sort them in a tree fashion. So we've got 7. Now we need to worry about 23. So is 23 greater than or less than or greater than 7? It's going to be greater than, so it's going to go over here. That's pretty much it. So we don't have to worry about that one. So 151, greater than 7, obviously. Is it greater than 23? Yes, so it's going to go on the right. It's 151. And these are actually the numbers for the Pokemon. And as we kind of progress into this, I'll show you what's going on. So number 4, we've already got 151 taken out. We've got 4. So 4 is going to go right here. Now we don't have to worry about that. Then we've got 1. Is 1 greater than or less than 7? It's less than, so we go over here. Is 1 greater than or less than 4? Less than, so it's going to go on the left. And that is a tree data structure. And if you want to add like any more to it, it's not that difficult. So let's just say you want to add, let's just say you want to add 6. You would go down here. You go, is 6 greater than or less than? It's less than, so it's going to go over here. Is it greater than or less than 4? It's greater than. You would go here and you would add 6 there, but the algorithm we're about to build, I don't know that Pokemon number. These are all correlating to Pokemon too, so I don't know that number. That's just kind of like something I did off the top of my head. So relatively simple, and it uses recursion, and I think that this is actually a good way to actually begin learning recursion, actually, because it's so elegant, and we could go through all types of cheesy examples, but sometimes it's good just to kind of jump in, and I'm going to explain to you how recursion works here in a second. And recursion is like the place to do to use in trees. So we're going to go binary search tree. We're going to make a folder, and once again, just in case you didn't know this, all of these are going to be individual nodes, and we're going to actually have like the binary search tree class, but we also have nodes as well too. Like these, what gives the tree its power is kind of like how we build the nodes, and those, like I said, the nodes are those little circles that we drew. So we're going to go here, we're going to add tree node. If I can spell it, we're going to go tree node. We're going to go in here. We're going to go binary search tree. We're just going to call it a binary search tree. And as always, going to name these public. Good old Visual Studio 22. Okay. And it's probably better to start with the node. Like I always think it's better to start with the nodes first. And the node is actually the most complex part. So we're going to have a key because this will be our Poke ID. This will be our Poke key. And this is going to be like a very generic one too. You could call this Pokemon tree or Pokemon tree node. And you could do all types of special things just for Pokemon. But there might be people coming in here who just don't want to do the Pokemon thing. And they just kind of want to know about tree nodes, and we'll make this tree very flexible and easy to understand. So we're going here. This will be our tree node, and we haven't actually, let me see here. Yeah, this is it's going to be self-referencing. So it's going to be, we're going to have the left tree, and I think a better one would be call it left tree, right tree. We call it child, but yeah, actually let's call it child because I think that that's more representative of what it is, because it is a child. So we'll go here. We'll go right child, left child, right child. So we go here, CTOR, and we're going to create, whenever this tree node is actually made, we're going to initialize it. We're going to pass in a string, we're going to pass in a value, and we're going to go down here, and we're going to init this stuff down here and pass it up into our properties. So if you don't know what's going on here, basically whatever we pass into this and whenever we create this, it's going to go up and it's going to pass it up here, and we're going to have this throughout our program, and we can utilize all these other properties. Otherwise, we would have to initialize these after we knew it up, and I don't think that that's probably the best idea to be. I think it's better to, this is, in certain scenarios, it makes more sense to create the value kind of like as we go. So go in here, and this is going to be, let me see. So this dot key and this dot value. Oh, sorry. This should be value right here. I think that that's probably a better way to describe it. We could just call it a string, but I don't know. I don't think that's right. So what's going to happen? This is going to pass down to here, and this is going to basically insert it up into our properties. And that's the entire reason that that thing exists. So now we're going to go and let's actually work on our binary search tree. So the binary search tree is going to be really easy to make in terms of properties. The most of the heavy lifting in terms of the operations on the data and the actual manipulating the data are going to be housed within the tree, and most of the actual data stores are going to be held within the actual node. And we're just, even though this is going to initialize this null, I think it's better just to have that null in there, and we don't actually need a constructor. So first thing, because this is recursion, we're going to split this up into two functions, and I'll show you what I mean here in a second. So we're going to go insert, and obviously we're going to have to insert our key, and we're going to have to insert our values, so we can kind of just off the top of our head realize that we're going to need those two values. And then we're going to have our root, and we are going to insert the item into our root. So root dot key dot value, and this is really important. You may be wondering, well, like, are you just going to insert everything into the root? You will understand here in a second. And this is like I said, this is a good introduction to recursion. So we're going to go public. We're going to go tree node. We're going to go insert item. We're going to insert that item, and it's going to return a tree node. So then we're going to go tree node. We're going to go node. We're going to go int key, and we are going to pass it as string value. And we're going to go down here. So just like our other data structures, we're just going to go in here, immediately new up a node. So you got to remember that these nodes are objects, and we're tying them together very similarly to a linked list. And you're going to have to insert a node into the beginning anyway, so you might as well just new it up and just create it immediately. So we're going to go if node is equal to null. And basically this is saying and the only time the node is ever going to be null if this is the first time you insert, essentially. So if there's nothing there, if this is the first time you insert, create the root. And I may have called it a node before, but this is actually where we're going to create the root. It's going to go, node is equal to new node. So essentially the node that we pass in here is going to equal the new node, and that's what we're going to be returning. And then we're going to return that node so that it can be inserted into the root. Awesome. So now what's going to happen is if this isn't the first insert, traverse, this will be our first traversal into trees, which is a very good thing. Traverse find null insert. So what it's going to do is, let me show you. It's going to go, is this left or right? Or if this is a node. So if it's a node, I'll show you. Essentially, it's going to create it, and we can just redo this right here. I'll actually just step through it one more time just so we can kind of get a better handle on it. So 7, and I X'd them out, but just imagine that they're not. So the very first one, it's going to hit that first if statement, and then it's going to create it. So now we already have our 7. So what it's going to do is it's going to check this node, and if this node is greater than or less than, it's going to insert it based on that. And if it's greater than, it's going to bring it down here. So let's see. Let's go back in. Oh, and just to reiterate, if it finds a null, remember, like right here, we actually have nulls right now. And what it's going to do is it's going to traverse, and it's going to find that null. If the null is greater than or less than, it's going to insert it into that null. So go back, and let's start working on it. So if the key, essentially the number that we passed in, is less than the left node, or the node dot left child, or the node key, I'm sorry, so node key, because we're actually comparing that, we're comparing the key. So if the key is less than, go into the node dot left child and insert the item. Isn't that cool? So we're calling a function within a function. So we're gonna do, we're gonna do the left child, and essentially it's gonna keep checking. It's gonna keep checking. It's almost like having a small state-driven for loop. If I could describe it as that, and I'll show you why it's so elegant here in a second. And we'll just kind of step through this, and this will be a really good introduction to recursion, and it'll be interesting as well too. So we'll go right child, then we're gonna go insert item. And as you can see, that's the reason that we have this in here, because if you had all of that in there, if you tried to put all of this into one function, it would look like doo-doo, and I don't even think it would actually work. Like I don't know how you could, because I actually tried to code this up without having that function in there, but I don't even know if you could actually get it to work without it. So we're gonna go key dot value, and essentially it's going to keep going through, and whichever one, it's going to do that insert at like whichever state that we are at. And then here, if not, we're going to return the node. And this will just be like a base case to prevent this thing from having a stack overflow. And that should be our insert. So we'll go in here, binary search tree is equal to BST is equal to new binary search tree. We're going to go here, we're going to new this up, and I'm going to go in, I'm going to add these values. So 7, 23, 151, 4, 1, and we've got that 6 on the end too. We can just add the 6. So here, got binary search tree, and then we newed it up. We're going to go insert. We're not going to do insert item because the insert is like the public facing, like API, in order so that we can use the recursion. And Pokemon number 7 is Squirtle. So we're going to go Squirtle, we're going to go BST, we're going to go insert, and then Pokemon 23 is Ekans. So we're going to go Ekans, we're going to go BST.insert, and we're going to go 151, and that's going to be Mew. Then we're going to go BST, then we're going to go insert again. Then we're going to go, let me see, 4, we're going to do Charmander. Okay, so we got Charmander, and then we got BST.insert, and we've got 1, and of course number 1 is classic Bulbasaur. And I haven't spelled Bulbasaur in a long time, but we'll just go with that. Okay, so we don't even need to traverse anything, and we don't need to iterate. I think it's oftentimes better just to hit it with the debugger and look at it through there. So let's go ahead. We've got a watch. We've got our watches set. So I've already got my watches set beforehand, but I suggest go down here, right click, click add watch, and we'll go ahead. We'll start stepping through this thing. So it's going to assign that null. And right now our tree is like 100% null, but watch what happens when we actually create it. So that first BST is created. Now our actual tree is created, but which this is our tree, the BST, and then but now we don't even have anything in it. So watch what happens when it first goes in. It's going to go root. It's going to go down here. It's going to go ahead. It's going to new up that tree node. Then it's going to hit this. If this is the first time you insert create the root. So we're going to go into the node, and then it's going to assign that root. Great. So next, we're going to go in, go here. Now we're going to go into insert item and watch what happens. This actually isn't a good representation just yet, but as the tree gets bigger, you'll begin to notice recursion, and it's really cool. So it's going to go the right child, and the Pokemon that we inserted was Ekans, and that is the right one. So 23 is next, and we inserted into the right side. Let's go. Let's keep going. Let's see. So it's going to return our node. We're going to go down, and you will see here. So our right child is Squirtle. So our first one is Squirtle. So Pokemon number 7 is Squirtle. Then Ekans is 23. Then it's just going to keep going down. It's going to go insert. Let's see. Let's watch this recursion. So it's going to go to the right child again. Then it's going to go back, and it's going to go back to that insert. It's going to run that function again. We're now actually doing recursion. If you look into recursion, this function is just going to keep being called, and it's going, whenever you see recursion in a tree, that's how trees are traversed. And you can see how elegant this is. So if the key is less than, it's going to essentially just keep moving down the left side, and it's going to keep track of all that state. And once it actually returns, it's going to go back up, and it's going to return the element to the one that we want to. So it's going to go down here. It's going to go down to the right child again. It's going to return that node. It's going to go again. It's going to return that node. It's going to insert it. Then it's going to keep going down. And you can see here, we've got 151, we've got Mew, then we've got Bulbasaur, and let's put in a Joker value so that we can actually see the whole entire tree. Otherwise, we can't see Bulbasaur. So I'm going to go down here, and we've got our whole entire tree. So we've got left child. We don't have a left null child because, let me see here. Let's just go ahead and build out this tree again. So go back. We're just going to rebuild it really quick. I'm just going to fly through this thing. So 7, it's going to be 23, then 151. We're going to go here. It's going to be 151. Then we're going to go 4. So then we're going to go 1, and 7 is greater. Then we're going to go 1, so 1's going to be right there. And then we have 6, so 6 is less than, and 6 is going to be on that side, just like that. And that's a good representation of our tree. And let's go ahead, let's go look through all the childs. So we've got left, and I'm actually going to bring it up. Let me just bring it up right here, if I can move this thing over. Sorry, my voice is starting to go again. The streaming hurts like my voice so bad. Okay, so we've got 7. And I actually can't bring this up. I'm just going to bring it over onto the other screen and check it. So we have left child. It's got another left child. Looking good. Then we've got right child. Got another right child looking good. And that is pretty much it. That is our insertions. Now we are actually going to do a find. And a find is another good example of recursion. And a find is going to be the second method that you're absolutely going to have. So logically, let's just say we are going to try to find Mew in this case. And just like the insert, what is going to happen is it's literally just going to traverse it. It's going to go here, it's going to go here, it's going to go here, it's going to search for mu, and it's really not that much more difficult. And we're going to house this find underneath this insert down here. And let's go ahead and code it up. And if you guys already understand like how the tree traversed, it's really not going to be that much more difficult. And it's going to be, like I said, it's going to be a piece of cake. So just kind of hang in there. I know it's probably getting a little boring by now, but the only two methods that you need to know are these, and you'll have a good grasp on these topics. So we're going to find, and we're going to pass in the int because we're going to find by the int. Then we're going to do the exact same thing. We're going to go tree node is equal to node. And we're going to go node. We're going to do this node right here. And we're going to go find. We're going to do the exact same thing. We're going to go find in here. And we're going to search for the root, which is the one in this case we're searching by the root, because if we've already inserted it, the root's going to be up here, and it's going to be Squirtle. So here, and we want to make a ternary operator, because if we can't find it, we want to have this down here, because we're going to return null instead of a string. And we're going to get a couple errors down here, but I wouldn't pay attention. I wouldn't pay too much attention to those. So we got find. Now we need to actually create our find function. And for this one, you could make it private. Actually, let's just make it private. It's a private API. So we're going to go in here. We're going to make this nullable, because this could actually return null. And we're going to do a find. And for this one, we're going to pass in that tree node. We're going to do some method overloading. So C# is going to be able to distinguish between these because we're doing method overloading. And we're going to go in here, we're going to go node if it's null, or if the key is equal to the key you found it. So it's basically saying if you land on this and the node is equal to the key, like you've pretty much found the node. So we're going to go in here, go key, and IntelliSense fix that. Then we're going to pass in the actual key that we put into the function. So go down here, and if either one of those occur, we're going to return the node. So now we're going to go through and we're going to do a couple else ifs. So we're going to go else if the key, and very similar, we're going to actually do our traverse. So we're going to go node.key. If it's less than, we are going to traverse the left side. And it kind of makes sense. If the key is less than, start going to the left. So we're going to go left, and we're going to pass in that key. Now we can go down here, else if, we're going to do key. And the find is way easier than the actual insert. So if you've made it through the insert, you're doing really good. So I'm going to go here, go down, and then we're going to go return find node.rightChild is to the key. Then all else fails, return null. And that should do it. Let me see here. So we're going to go here, and we're going to go bst, and we're going to console dot right line, and then we are going to pass in mu, and then it is going to return the value that we are searching for. So bst dot find. We're going to pass in that integer value. Okay, let's go ahead. Let's run this thing. We're going to go down. We're going to go into. We're going to do the find. So we're going to go down here. It's not null, so it's going to start traversing. And it's the right child because it's bigger. So we're going to go up here, keep going. And let's see what node that we have. Great, it has our mute. Anyway, that's pretty much it. Those are going to be insert and operations for a binary search tree and trees in general, and that's probably all you're going to have to know. Even for, we're going to have to talk about different types of traversals next, but just for basic knowledge, that's pretty much all you guys are going to need to know. Anyway, hope that you enjoyed this. If you did, make sure to hit that like button, make sure to hit that subscribe button, and as always, thank you for watching.